Hello everyone. Today I'll be discussing about the historical aspects of mathematics. So before diving into the right into the topic, I thought we'll just have a little discussion about what exactly can we think of what is history of math with regards to
Mhm.
math. So uh, so okay, pardon my writing, please.
No problem at all. We can understand.
Yeah.
Yeah. Um, so history of mathematics. When we think of history, we usually by definition, it is the study of the past events.
Mhm.
But in context of mathematics, is there anything of the past? Because mathematics as a domain has been the oldest and yet the most current in its form, uh,
Mhm.
right? So, uh, so whatever there was in the past is still relevant today. So it's not dead yet. It's not right in the past. We can still pick any part of the history of mathematics and think of it in a different way and prove some results in a different way. Might be a longer way, might be a shorter way, but we can still think about them, right?
Mhm.
So when I look at it, I think that a history of math can be more precisely said to be as the history of mathematicians, because the development of math has been possible because of them. So today, if we think that all of the mathematics which we are studying could not have been done handedly by a single person,
Right.
Mm.
uh, right? Um, so let's say that even today, if we start building mathematics, it will definitely take thousands of years to come to the point which we have reached today. So the history of
Right.
math is basically the history of mathematicians, and that's how math has developed. Uh, so with that, so the evolution of math is driven by mathematicians.
Mhm.
Now, when we say that, so why should we study what the mathematicians did? We are we can easily just study whatever developments have been made, and we can move ahead with our research. So why should we go on to study the history of whatever has been done? So I would like
Mhm.
to ask you all that what do you think? Why should we study history? What motivates us to study history of mathematics? If any of you want to tell anything about that.
I think one of the reasons which where I find it very interesting to delve into math history of in fact any subjects is to understand um, the fundamental points from where it all started. Why? So, if you are studying, let's say, algebraic topology, right? We are studying geometry and shapes, and so what is the need to first of all study it? That
Hmm.
takes us to the thought process of mathematicians. So, why in the first place they thought about it, and that
Hmm.
is very interesting. It also gives us the understanding of if we need to think of um, let's say connecting different topics. So
Hmm.
if we can understand the thought process of the uh, discovery of different fields or domains, then we can also it's very inspiring to uh, find out connections on our own and build probably new maths on our own also.
Yeah.
So I mean, one of the reasons I would think is, I mean, historically itself, if you look at it, well, let's sort of say physicists and mathematicians, because every great physicist has definitely contributed to maths also in a way. So, I mean, if you look at it historically, at least from the little history that I have seen, um, it's usually where one scientist. So if there's this, like say Newton, so Newton did fantastic work and so on, and then many years later, Einstein came along. He read through Newton's work, and
Hmm.
he saw that there are some things that this guy is taking for granted, and he said, well, like, maybe if we remove these constraints or conditions given, we get a more generalized theory. And basically where I'm going is, it's, you look at their work and we have to build up on the work which is already there. So uh, so it is very important to like get to know what they have done and why they thought like they did. And let's not call it mistakes, but we can definitely build up on whatever they have missed.
Hmm.
Because
That's right.
at whatever for whatever reason, maybe at Newton's time there wasn't really the differential geometry and all these are new tools that we have, that we develop from any field. It could be from chemistry for all but we at today's day and age, we might have new tools, and when we go back and look at their work, we can see, oh, like this adds up to Charu's logic, where you can connect different things even more. Like it's a very good connecting potential
That's
sort of
right.
thing. Yeah.
Yeah. In fact,
Yeah, right. And
Yeah.
yeah, go on, go on.
in fact, to add to it, just to give an example, how we understand about space and time, right? Newton
Hmm.
thought of it like absolute space and absolute time. So if we read how Newton really thought of what is absolute space and time, and then from there, Ernst Mach developed the idea of no, it should be all relative. There is no absolute space and time as such. That actually was an inspiration point of inspiration for Einstein, and from Einstein wanted to incorporate this idea of Ernst Mach into the relativity, and that led to the development of general theory of relativity and special theory of relativity. It gives us an understanding why studying and building upon, like Abhiram mentioned, upon the historical previous ideas is so important.
Yeah.
Srinidhi, you were saying.
Yeah, right. So, I mean, in the current era, we always look at advanced topics and advanced research. But I think history plays a major role when we start talking about the fundamental topics. So, questions like, uh, so let's say we have the Pythagoras theorem. So we have a square plus b square equals c square. Now
Hmm.
we generally just use it, and then you just use the formula, solve problems, and just go on with it. But once we start asking the question, why should a square plus b square equal c square? And that is where history comes in, and that is where we need to probe into the more, like, we need to probe at the most fundamental level. And it's not only with math, it goes into other fields as well. Like, for example, I always wonder, we have different computer programming languages now.
Yeah.
In this era, what we're doing is we want to learn more languages. We want to learn Python. So I mean, as and when we have some new computer language, we want to learn it, but no one really talks about how these programming languages are themselves made, how they created in the first place. Now, when programming came into being for the first time ever, so the thought process that has gone into that is is on another level, because what we're doing now, as Abhiram mentioned, we're just
Hmm.
building on whatever has already been done. So I think once we start probing into the historical aspects, we can actually channel those ideas into understanding how these fundamental aspects came into being, and that is where I think real research even lies, advanced as well as at the fundamental
Yeah.
scale.
Yeah.
Hmm. True. So as we discussed just now, we can make connections, as Charu said. Then, as Abhiram said, we can build on those connections, some that were missed while they were being worked on. And as Shinri said, we can appreciate how the things how the different concepts came into being. Yeah. So, yeah. So mathematicians initially, wait, I just need to draw a picture. 1 second. So I look at it this way. Let's say there's a cloud, and so this is the cloud of all the ideas. So basically, when scientists and mathematicians, physicists, when they were not called so, when they were working on all the aspects, they just had a few observations, and they just went along with whatever observation they made, and from there they got an idea. So I'm just roughly speaking. So they got an idea, and from that idea they proceeded to work either in the direction of physics, either in the direction of mathematics or other field. So they were not exclusively working in just one domain for a very long period of time in history, right? So there were many ideas, and it was actually not until, I think you guys know that it was not actually until 19th century, especially in math, when specific ideas were considered, and only so those ideas bloomed into particular domains of sciences, like math as a proper science bloomed after 19th century, when it became more abstract, and the whole set theory and everything was put together, and um, everything was defined properly. So it moved from a utilitarian part to doing math for its own sake, and then to a proper science, so that more can be developed on it in a more organized way. So so uh, so I'd like to continue by so till 17th and 18th century it was going on in different directions. It was in 19th century when this started happening. So in 19th century, the credit goes to a mathematician after whom all this started happening. And I'd like you guys to guess who this person was. I'll just tell his story, and if you can guess, then that'll be nice. So this person is actually known as the, okay, I won't give that away. So so let's say, so this is a circle, and so now I need to construct a 17 gone. So I need to construct a regular polygon with 17 sides. So is that possible?
Like using
Yeah,
like a compass and
yeah,
all that
it
stuff.
should be constructible from three point of
like
view,
the whole
with a compass and a straight edge.
Okay. Okay. Uh,
So if you think of, I mean, if you take, let's say, a triangle, how do we construct a triangle? Or a square? I think square will be the easiest. So if we take the diameters of the circle, and then we can connect the, let's say, orthogonal diameters, right? So then we'll get a square using those 4 points. So maybe if we can, if we have a square, then we can bisect those two, uh, the sides, all the sides. That gives us, I guess, an octagon, right? So we can increase it by 2
Possible.
probably.
4 is possible.
4.
8, yeah.
And then
16.
Then
16, bisecting
yeah,
all of them.
16.
So yeah.
Mhm.
Yeah, so this is possible.
Mhm.
But then what about 5? Is 5 possible? A pentagon?
Uh,
5, 7, then 11, 13, and 17. Are these possible?
I mean, can you like instead of a square, we construct a rectangle,
Mhm.
and on the rectangle we construct another triangle. I mean, we can construct a rectangle, right? I mean, I'm not really sure actually. So
Using
yes,
it should be possible. I think if we
a
take
square, then
So we are considering regular polygon. So all the
oh,
sides should be
Mm.
that way.
equal.
sorry about that.
Yeah.
So we are just looking at a case where regular polygons of certain number of sides, are they possible or not to construct
Okay.
with just a ruler, with just a straight edge and a compass?
Uh,
So we'll have to then divide the circle in 5 equal parts. So if we can do that 5 equal points, then we'll
Ah.
get a pentagon.
Yeah, so 10 is also possible.
yes.
Right.
Mm.
So 3, 5 are done. So do you guys see any? So 3 is done. We saw that 4, 8, 16, all these are possible. Then 5 is also possible. Then from 5, 10 is also possible. And 20 is also possible.
Right.
So we see a certain pattern that if we know this, we can create multiples of this, right?
Right. Bisecting each side, we can have.
Yes. Yeah.
Okay. So if
But
you have a
what-
triangle, we can have 6,
6,
Yeah.
12.
yes.
Okay.
12 is also possible.
Mhm.
But then what about these numbers? They don't, so these are rhyme numbers.
Hmm.
So what
Mm.
about them?
Uh,
So we need to find out if we can divide it in equal 7 points and so on. But how do we go about doing that? Using only compass. That's the
hmm.
restriction,
Yeah.
right?
So
Because at that time only these tools were available,
yeah.
right?
So
Early 19th. Mhm.
so during the time, so the Greek mathematicians were very strict in, so they wanted the constructions to be extremely pure. And their idea of purity was that the construction should be done only with a straight edge and a compass. No other tool should be used.
Mhm.
That was their idea. So, considering their idea, is this possible? So, actually, the solution comes in a very funny way. So if I go on to draw it right now, I won't be able to draw that. It's a very difficult process. I can't even make sure that if I've done the right process or not. But uh, the state, uh, the statement that yes, a 17 gone is constructible, that was proved, and that was not proved from geometry point of view. That was actually proved while studying a different problem in arithmetics.
Is it? Okay.
Yeah.
Mhm.
So, um, hmm. So x raised to n equals to 1. So this is an equation where we study, we are basically looking at nth roots of unity.
Right.
Right.
Finding a solution for this, a mathematician, he came upon, or let's say he discovered that yes, a 17 is constructible. Uh, so, so this is a circle, and so if we consider this equation, we can say that we want a length which will be 1 by 17th of the whole circle, so that we can divide this into 17 parts. This whole circumference can be, so the circumference of the circle can be divided into 17 equal parts,
Right.
so that we can join those
Hmm.
dots and make a polygon with 17 sides. So we can say that 2 pi has to be divided into divide by 17 to get that length. Now, how to get this length? So, we consider this angle. Now, by trigonometry, we know that this angle will be cos of 2 pi by 17th, right? So, basically, we need to check that is this number possible? Is this a finite number which can be put to length, or which can be considered as a constructible number? So a constructible number, by definition, was that something which could be combined, a finite quantity which could be easily combined by addition, subtraction, multiplication, and division. That's a constructible number. So we need to find something which, a number, a formula which gave the length of this. So now we know that's possible with a calculator, but this is happening in 19th century. So at that time it was not possible. So this was calculated by a mathematician, and the proof is very long. I won't get into that right now. So his idea was, he was working on this nth roots of unity. So he looked on, so while considering nth roots of unity, he considered this equation, x raised to 17 minus 1 equals to 0. He wanted to find a solution of this. So while finding a solution of this, he constructed this circle and looked through. So he combined his knowledge of algebra with geometry and looked at the problem like that.
Right.
I hope I'm making sense. So that was what he did, and the Greek mathematicians, they from the geometry side, they had concluded that 2, 4, 6, 3, 4, 6, 8, these are the only, and the multiples of them, these are the only possible constructible regular polygons, and no, and 11, 13, the polygons with these primes are not possible to construct. They had concluded that. But after 2000 years, this mathematician showed that this is possible, and he went on to show that not only this, but there are many more primes which whose polygons can be constructed. And those primes have a special character. So, so do you guys know of Fermat numbers? So a Fermat number is of the form this.
Mhm.
So Fermat basically told that um, this so whichever number in this equation, whichever number comes up as a prime, that prime is possible to construct.
Oh, okay.
Hmm.
So let's say I put 4 here to or let's say I put 1 second, I'll just put 2 plus 1. So this will be 2 to the power 2, 4 to the power 4, 16 plus 1, 17. So this is possible to construct.
Mhm.
Okay.
So whichever prime comes up in this equation, so basically Fermat prime numbers are possible to construct as a regular polygon. So this whole idea was given by a mathematician who made arithmetic a pure mathematical science.
Mhm.
So before him, there were many results on arithmetic, but they were all spread out. They did not have a combining theory. So this mathematician wrote a book in which he rigorously proved all the results of mathematics or arithmetics and combined them and raised arithmetic at par with geometry and algebra, which arithmetic also came to be known as a proper mathematical science after his book. So,
Hmm.
and
Okay.
he is known as the Prince of Mathematics. And the book he wrote is called Disquisitiones Arithmetica. And he was so excited by the result that nobody could prove that a 17 gone is possible. But I can show that it's possible. That he told his colleague that when I die, please write the proof of please write the proof of 70 the theorem of 17 gone on my tombstone. He was so happy with that. uh, and so he is considered the greatest of all mathematicians, and he basically stands at the tip of this changing period when we were going from 17th century, 18th century to 19th century mathematics, where we were all the abstract part and we were organizing all the mathematics into proper categories. So can you guess who he was? I've taken a different result of his. If can you think who was?
Is it Euler?
No,
Oh.
after him.
Oh.
Oh, is it Gauss?
Yes.
Oh, okay.
Nice.
Mhm.
So it was Gauss, who although whose methods were of 18th century, but then by the time with time he adapted 19th century ways also. Now why am I saying like this 18th century ways and 19th century ways? So basically there is a big difference observed by some historians in these two periods. So initially this domain of mathematics was in the hands of a select few. So only few people like Archimedes or Newton, so they used to practice this science and they used to complete their works and publish them,
Mhm.
and discuss with a very few people whom they consider to be at a certain level. They never taught their works, right? They never discussed it with other students or who might be interested in that.
Mhm.
But in 19th century, this started happening. So the mathematics domain or the physics domain did not remain exclusive to a select few, but the interest grew, and
Mhm.
the uh, so it was actually they actually wrote it in. So the mathematicians from here on tried to write their work in such a way that the people, so the following generations could also follow their work. So they try to prove it. They try to make logical connections so that everybody could understand. But before that, even Gauss, so the proof of 17 gone, he didn't care to write it himself. He just told that, yes, I've proved it. And he showed the equation.
Mhm.
But he never showed how he came up with that or the proof of it. After 40 years, it was another mathematician who showed that this was how he proved. So they didn't make public whatever they worked on. So in 19th century, it was when this started happening. So this is where the difference came. The whole idea of creating their work only for their own satisfaction or to continue it for generations as well. So that started to come in.
Right. It's
And
more in the spirit of inquiry that they would do. I think about Gauss, he used to maintain a scientific diary for himself from very early age, and he did
Yes.
not really care to publish his results at all.
Yeah. Yeah, exactly. So he had a diary which the historians found upon very later in time, and they told that he kept a lot of results to himself. If he would have published all those results, so in 1800 only, he would have we would have a lot of mathematics which was later rediscovered.
Mhm.
So we would have been much more ahead of time if he would have published all the results which he came upon earlier.
Right.
Yeah. So so before 18th century, many of them had this idea that we will publish. So Gauss had this motto: I will publish only those results. I will publish few but ripe results.
Mhm.
So they
Hmm.
wanted to publish something from which nothing can be added and nothing can be taken away. His motto was few but right. So whatever things they found that no, this is not complete, they never published it. They just kept it to themselves. So even others could not build upon it.
Mhm.
Yeah, so that was the case. And so the credit of giving arithmetics this level goes to Gauss, and to him, arithmetics was his first love. So he had this quote also that if mathematics is the queen of sciences, then arithmetic is the queen of mathematics.
Mhm.
Yeah. And can you guess what was his age when he actually proved 17 gone and he published his book? Um,
17.
20.
Very young guy, I assume. Like he's like
yeah.
15 or something.
So he was 19 when he proved that. And when his book was published, he was 24. And he was working on it since the age of 21 on the book. So it took 4 years to publish that book, to make it a complete work by himself. So
Hmm.
it was a completely individual work. So Gauss didn't even try to read the So he read very few works of other mathematicians. He just wanted to build everything from without taking any influence of others.
Right. I think this adds to one of the questions that you asked in the beginning, right? That why should we study history if
Yeah.
probably if we build everything from scratch, we may get different methods of studying the same fields, which already, I mean, different from the already existing methods, which may open up some new avenues also.
Yes. So this actually gives us two sides of people. So some people's works are so dear to them that they don't want it to be touched by anyone else, neither they want to be influenced by anyone else. Because purely mathematics is seen as uh, an activity of human mind. So we don't, not every time we observe it in nature, we just do it. uh, so it goes on to a very philosophical thinking. I don't know how it's done, but it's something which just comes to us on paper pen from our mind. So so some have this mindset that we don't want to share that, and some want to share it and make it and so some work on it for the sake of their own satisfaction, and some work it for the sake of the whole development of that science.
That's
So
right.
we can think
Yeah.
of it right, what is better, what the development of that field, or is it a personal endeavor, an individual endeavor? uh,
Uh,
because mathematics is not always applicable. We can't always apply it to certain theories. We pick a few concepts or theorems from it and use it in physics, theoretical physics, and everywhere, but not all parts of it. And so we can't say that all of mathematics is relevant to our studies in different sciences, but still some people continue to do it because they like that train of thought in their mind. So
Right.
I mean, the question that you asked, like, should we do it for the development of the field itself, or for our sort of, I don't want to say satisfaction, but for our, let's say, uh, chase, like to find out the truth, I guess, eventually. So me personally, I feel like uh, a sort of like both cases, but I'm a bit more favored to the Gauss's way of thinking. Uh, I mean, it is like maybe everybody can't think. I'm saying like based on the work that somebody puts out, it might not always be appreciated at that time, because people will only understand the importance of the work like maybe 100 years later. And like I don't know, it is meant to be appreciated, and because it is like it's the truth and all that, like it's so if it is only appreciated by you, and if it is sort of degraded by others, it isn't really right. For the piece of paper itself, the paper that you've written, it isn't right, because just to be appreciated. And you never know like when it will be, because like even Einstein was criticized heavily for his work and his thought process, which didn't really do him good, right? I don't know, I think he went down a bad spiral around that. And later, yes, they all joined, and they realized the importance. But uh, I don't know, like if I feel like if you can appreciate the truth, then it's good enough for the field itself. Doesn't have to be appreciated by everybody else and things like that.
Right. I think to add to what Abhiram is saying, it's more like taking, the if we ourselves have this idea of, getting closer to the truth, so it may eventually lead to development of the field. But
Yeah.
if keep in mind already that development of the field, maybe we may publish some results like Gauss. He wanted to publish only the ripe results. So
Yeah.
very so completely that the results that completely changed the fields, right?
Hmm.
Because anyways it took us closer, one step closer to the truth.
Hmm.
So even if someone like Feynman never used to publish his results. He would just he developed the field of quantum electrodynamics. He would do all the things on boards and would just simply erase it for the sheer joy of it. And
Yeah.
his students then started noticing, and they took his help and started publishing what his results were. So
Hmm.
when we do it for the sheer joy of it for going closer to the truth, I think it eventually maybe it gets delayed, but it eventually gets takes the whole field closer to the truth. Yeah,
Right. So you're saying, in some way, even if you work on it for personal satisfaction, it's gonna eventually end up changing the field.
that's right. Yeah.
That's,
Yeah.
that's nice.
Mm.
So actually, they are. So both of the things are connected with uh, the idea that we are working on it.
Right.
So the work is important.
Yeah.
If we collaborate with someone or if we do it by ourselves, we should move on in that field. Later or sooner, that will be put to some use.
That's right. Yeah. In fact, Gauss was always working. He was very interested from the early childhood in maths, and I think his he developed very early in during his school time itself. The
Hmm.
this errors that we find in observations, experimental observations,
Hmm.
that actually led to one of the very remarkable applications. So at that time, telescopes were so we would observe any planet or stars, and
Hmm.
we would sort of track them through observation. Like today, we didn't have CCDs and all the sophisticated instruments, right? So
Yeah.
we found some star, and during the daytime, because of sun, it couldn't be tracked, and they lost the track of astronomers lost the track of the star, and they were not able to find it purely because there was error in calculation. So they used the method of what we call today RMS, finding the RMS error, that was developed by Gauss, and
Oh.
because of it they could track back the planet that was sort of lost. Yeah.
Hmm.
So his idea was always to just do maths for the sake of it, finding out things and writing in his notebooks, and that's it. And it has taken us to really like it has progressed because of his work. Even Einstein's work is sort of based on what Gauss had developed, which eventually led Riemann to
Yeah.
develop Riemannian geometry and so on. Yeah.
Yes.
Mhm. So I think this was a really good session. So we'll have the call again.